Alright folks, welcome to another video on induction machines, and this is on simulating an induction machine, and we will go over a very simple approach to simulate an induction machine. No reference frame transformation for now. So if you remember, we looked at our modeling schemes, right? And we said from our equations, so voltage equations like this, right? And we transformed our rotor circuit from the we transformed the rotor circuit from the rotor side to the stator side, and we used the prime VABCR prime variables to illustrate that. And we said we can use this transformation, the stator number of turns and the rotor number of turns, to transform those rotor variables to the stator side, right? And these prime variables indicate those transformed variables to the stator side. And these are our matrix, the inductance matrices. We have the motor position considered in the inductance calculation, and that is the model that I use in order to build this in Simulink. Okay, and if you need any parameters to simulate with, you can find them on the Analysis of Electric Machines textbook, or you can contact me and I can share some parameters that you can use. All right. Now, and of course, if you need to characterize your own machines, we talked about that in one of the previous videos. So feel free to go through that. But this is the model that we are going to use. And since we are going to apply voltages, our rotor voltages are going to be 0, right? Because we are considering a singly fed. And we are applying ABC voltages. We'll for now apply a fixed set of voltages, open loop, very simple control. And in order to do that, we need to, if you are measuring or if you are calculating the currents, we need to find the inverse of this matrix and left multiply the voltages. Okay, so that's exactly what I'm going to do here. Okay, so let's take a look at what this simulation looks like. I'm using MATLAB Simulink. Okay, let's see. Yeah, that's not good. MATLAB Simulink, and I'm going to turn off my doc cam here. Okay, and I hope all of you can see this. All right. So I have this MATLAB function here, and then I'm in this block. What happens is I have the voltages going into it. And then, of course, we have the rotor position, okay, rotor position coming back. And this is the mechanical equation. This is the mechanical equation. Okay, we are familiar with this. We've seen this in DC machines. We've seen this in synchronous machines. We have two integrators. Since the output of the torque equation is acceleration, this is speed, this is position. Both are needed for the simulation. Okay, and then the output is the rate of change of current, right? Those IA dot, IB dot, IC dot terms, which we integrate to get the actual currents as states to be fed back. Okay, and then inside is the equations that I showed you along with the inductances and the matrices. And then we also have a torque calculation as the output. Okay, and let's go inside and let's take a look at what we have. Okay, all right. So I'm not sure if you can see these, but I have my inductances, the values here, poles, resistance, and all that. And then I'm defining the different inductance and the resistance matrices. Okay, and then simply I've set it up as a function with outputs and inputs. And then here I'm just doing a calculation, just using the matrices. Okay, and then I'm calculating torque based on those values, and then I'm placing them just at the output of the block. Very simple. Okay, it's in a script form, and I pass these parameters back, and this runs in a continuous loop. So let's quickly run this, see if this will run without a problem, and we can try to look at the currents and all that. Okay, yeah, it ran pretty quickly. So let's look at the currents. Maybe I'm applying open loop voltages here, and you can see this, right? So remember, we talked about at startup you're going to see a spike. Sometimes, depending on the machine size, this tends to be very large. This tends to be very large. Okay, but here it's not that big, and then you can see since the voltages and the frequencies are maintained at a fixed value, the currents are relatively staying at the same value. Okay, and then these are the rotor currents. If you compare them, see the rotor current frequency is very low. At the startup, it is fast because the motor is not moving, right? Remember, we said the difference between the speed of the rotor and the magnetic field of the stator is what defines the rotor flux frequency and the amplitude. Reflects it, right? So as the motor speeds up, the flux frequency drops, and you can see this when we look at the motor speed. See? Ah, very nice. Look at that. So initially, let's see what these variables are. We have the torque, that's the first one, speed and position. Okay, torque, speed and position. So let's see what we have. We have a lot of torque, right, at the beginning, and then we can see that the speed, it's accelerating, and then it comes to synchronous speed. Okay, and then position, it keeps on moving, right, keeps moving, and then here I believe there's a load variation. Yeah, so I have a load step coming in at that time, and what happens is this, because of the load, the speed drops slightly, right, and then you can see that in order to compensate, the torque will slightly increase. Okay, remember the torque speed curve, as it goes away from that synchronous speed to the left, the torque will increase. That's exactly what's happening here, right? Okay. All right. So I hope this is helpful in a very simple manner to simulate the machine. You can probe any variable. We are looking at just the simple torque, speed, and position. And now, based off of this model, you can build any complex control algorithm. If you want to do torque control, speed control, slip control, all that kind of controls can be developed. So I'll show you one such example. So this is, okay. So this is one example. So this is I believe this is volts per hertz control. Okay, volts per hertz control of the machine. And what we're doing is, this is an inverter. Instead of applying the voltages directly, we have a certain speed reference, a rate limiter, number of poles, which converts that to the amount of voltage applied, and then we use the frequency here that we want it to rotate at, which is kind of setting the position for the inverter. And this is the same motor model that we have. Okay, same motor model that we even used earlier. We have the mechanical equation, and it's taking slightly longer time because of all the calculations that it's running, but we should be able to see the performance. Okay, so let's see what we have. Oh, see, interesting, right? So it's ramping up very slowly because of the rate limiter, but eventually it's reaching, right? It's reaching the speed. You can change the speed if you want. Let's see if we can look here. See, very perfect sinusoids being applied, right? Let's see what we have in terms of rotor currents, right? So rotor currents, oh, very nice. See? You can see that they are still low frequency. Initially, you see a lot of current, but eventually they slow down. Okay, they slow down. They are very, very low frequency. If you look at the torque, right? See, it's maintaining torque at fixed value, and then you can see that it's somewhat changing after this. So this is after this reaching the synchronous speed. It's lower, and then when we change the load, it's following. It's maintaining the torque, and this is at the speed that it's the rated speed, or the speed that we are applying based. Let me try to rephrase that. This is the speed that we want, and which is applied based on the electrical frequency, because electrical frequency is what determines the synchronous speed. Okay. All right. So very simple simulation, and then you can develop advanced algorithms and control schemes based on the same model. Okay, same induction motor model. All right. All right, folks. Thank you again, and hope you enjoyed this. Please let me know if you have any questions, concerns, doubts, any clarifications, any errors I made, and I'd be happy to fix them and re-upload. Okay, I'm looking forward to your feedback, and if you like them, please do let me know that too. Thank you.